our nickname on IRC, so feel free to contact us if you have any question. So for GStreamer backend for Chromium, so objectives. So whenever you have a Vido tag in your page, we want to have a GStreamer pipeline. We want this solution to be generic and efficient, in a sense that we don't want to have anything hard-coded. We want it to work everywhere, and we want it to be efficient, especially on embedded platform. We want also this project to be open source from the very beginning. So it's important to understand that the initial point is actually no GStreamer backend in Chromium. And as soon as we had something, we have put this on GitHub, and this has been done in the last month, I think in June. So the presentation is divided in two main parts. The first one is about the Chromium architecture and how we integrate a GStreamer backend. And I'll finish this first part by a demonstration. And then second part is how we integrated the advanced feature, how we support media source extension, for example, using GStreamer, and how we integrate zero copy. I terminate also this part by a demonstration. So about the Chromium architecture, you can see it's mentioned on the main page of Chromium that the code base of Chromium is so massive that it's impossible for someone to understand all possible states. There are nearly 200 external dependencies, and a key point in security is understanding. So in order to so the solution for this is to split your application into multiple processes, and so that you can sandbox with a different policy each process. It's also useful for stability. The best way to fix bugs, but when the release is to the client, to the user, you have to minimize the impact of a bug until it is fixed. So in Chromium, you have four main processes. The main one, this is when you start your application, is a browser process on the top. This is the only process that can access the network and the files. You cannot access OpenGL. And then for on the left, for each process, for each page, each tabulation in your browser, you have a render process where lives blink and v8. So this is where the HTML and JavaScript is transformed to something visible. This render process per page doesn't have access to network or to GL. Everything is blocked. Then you have on the middle the GPU process, and we only one process like this. This is only process to access the graphic card. And then there is special handling for Vido, for the object tag, for the plugin. They are put in a separate process. So if you take the Linux kernel and you think about a set of all the system calls, this represents sort of surface for attackers, and you want to protect this surface. So you have a feature in the Linux kernel, which is the secure computing mode. When you start a process in this mode, it's simplified, but you can only access the exit system call. So you can do some processing, but then you can do only exit, you cannot open. Then you have an extension for this, is to, before starting the process, you can go to a big switch, and for the 300 system call, you say yes or no. You want to allow them or deny, and this is set for the whole lifetime of the process. But if you allow open, you can also attach a handler. So maybe you allow open, but you want to only allow to open a subset of specific files. So this layer of sandboxing is applied to almost every process in Chromium with a different big switch, different policy. For the render process on the left, so which is for each page, they also chroot to an empty directory. So from his point of view, the root directory is empty, and it has a different PID namespace. So whenever he gets access to kill, even if he has the PID of the browser process, it won't mean anything for him. So before to think about GStreamer, we need to know about the existing media backend. So on the top you have a Vido tag, and then you have a Blink interface, web media player. On the top left in green, this is a web media player for Chromium. This is the command path, and it uses the whole framework, which is on the left bottom. So inside Chromium, you have a full built-in media framework, so-called media pipeline sometimes, with some interfaces like Vido decoder, parser, demuxer, even so fake sync, fake source. So it's like GStreamer, and then you have some implementation. So for example, the VPX decoder, so they directly use libVPX, so for VP8, VP9. They can also use they also an implementation for ffmpeg, so it's like gst-ffmpeg, and also hardware decoders. So one of them, the API v4l. So this is the command path. Then for Android, there is something quite hard-coded in Chromium. So it's a guard. If define Android, do this. They're mainly not using this framework. They use the Android media framework. And so this Vido tag lives in the render process, but on Android, they forward everything to the browser process. So if we use GStreamer, we won't use at all this media framework. So what from that are the requirements for GStreamer backend? So we need to respect the sandbox rules. So we don't want to arrive and say, okay, disable everything. We don't want Vido hole. There's a punching technique. It's not it's not handled by any specification. It's hard to maintain. It's really not a long-term solution. It blocks the web. Lot of limitation with some 3D CSS transformation. We want to handle protected content. So we're going to see how that there are existing specification to handle this, and we want to support also zero copy. So where to put GStreamer? In which process? So render process, that's a big no. This is a place we want to avoid. It has access to nothing, so we won't be able to load some plugins, and we don't want to compromise the rest of the process. We don't want to be in a browser process. They use this for Android, but then we won't be able to have our sandbox policy, and if GStreamer crash, you just crash the whole application. Not in GPU process, because it's really intention for this process is to only access the graphic card. So the solution is a new process. We'll be able to have our own big switch of system call filtering, our own subset of files that we allow to open. And I'm going to show you how it can fit with zero copy G-copy. So this diagram is about the interconnection of the media process. On the left, bottom left, this is the media process. There is only one like this. On the right, on the bottom, you have render process per page. Whenever you have a Vido tag, it will ask media process to create a pipeline. And then the media process gets the data from a server, not directly, but through the browser process. And it will use GL not directly, but through the GPU process on the top right. So as we don't have access to network directly and no GL directly, we have to wrap the Chromium API that allow you to, for example, for the source on the top. So imagine you are from the media process, you can use the Chromium API to make a request to the browser process. I want you to open this URL. And so this is done through IPC, and you get back data through shared memory. So we wrap this into a GStreamer element. So we won't use SOUP HTTP source, for example. We use this new element. For GL, it's a bit similar, but it's not a built-in, so on the bottom, it's not a built-in element, but a built-in GstGL context. So we inherit this, and we call it GPU process. So in the normal GstGL, so out of Chromium, to use GL, so it knows about all the signature of the GL function. It just look up into the shared library, the libgl shared library, for all the name and get the function pointer and build a vtable on this. Here we don't allow to load this shared library, but Chromium provides you this lookup function, which is on the very bottom left, getGL function pointer. So we build our own vtable on this. So this is the purpose of the context here. And then when you really call GL function, actually call GL function, it's serialized and through IPC, command buffer and shared memory, and send it to the GPU process where the real call happens. And everything is asynchronized. So on the left, this is kind of the client-side API, and on the right, so for the client-side API, it's only GLES2, so they want in something uniform. But on the server side, for GPU process, they can keep GLES2 or translate it to a big GL through Angle. So this diagram, so in the middle, this is in blue the media process, and on the top this is the render process for the page, and this is when there is a Vido tag. We call, for example, play, and then this is forwarded to the through IPC to the media process. So all the function of the Blink Web Media Player interface are forwarded to an object in the media process. And in the media process, we use a GstPlayer. So in our solution, we want also to minimize the number of lines of code we use for GStreamer. And when you think about all the code that there is in GstPlayer, it's good that it's not in Chromium. But the good thing is that we know that it's done well. Okay. So the first demonstration. So I'm going to show you. So far we can with all of this we can have progressive and adaptive streaming and the sandbox. So I have prepared some stuff. Okay, so this is a page with 4 IDO tag and some pipeline. Okay. So I'm going to be quick because there is quite a lot of to show, but later I can show you again. So to prove it's really GStreamer, I have acted a bit and inserted a GL effect element. So if I applied this GL effect, you can see this is really GStreamer. So far I have disabled all the sandboxing. If we enable the sandbox, we have currently a problem about the audio. It just crashed on a system call, so on an open, and we suspect it's in the libc or something. But so I can show you. So this video contains audio and video. It just crashed after, during. So if you look at the backtrace, it starts from Pulse Audio. So Pulse Audio at some point do an open, and for some reason it crashed. So we have quite wasted time on this, but this is still pending. And for streams that contain only video, so I enable sandbox just to show you that with video it is working. So here, for example, if I hack the pipeline and I put a T with and I branch X image sync or something, like just to pop up here, it won't work because it's blocked. It can. And then I have also an integration with some CSS transformation. So here, for example, you can turn on the cube, which is it's fun for transition, but once you want to watch your video, just put it full screen. But it's to show you that it's correctly integrated. We don't break the web like a video, for example. I don't have the network set up, so this is on my local web server. Don't have network for HLS. I haven't managed to install it on my own server, so I just have the graph. So quickly, important thing is that here we see our source where we've wrapped the Chromium API to contact the browser process, get the data back. And on the very, sorry. So here you also see for HLS, for each chunk, it instantiates a new source element to get the next chunk. And sorry, on the right you have here, so we use GL image sync directly, and we see that we use the GL context GPU process. Okay. So far it's great, but if we go to YouTube, it won't play. You need to support more features. So one of them is a media source extension. So this is part of the W3C specification, HTML5 specification. It's an extension to the video tag, and it's a JavaScript API. So here you have an example of a JavaScript line. So this allows the application to control the fetching and the buffering. So you have access in JavaScript to your buffer. You have your source. You can add a new source buffer for audio, for video. And in Chromium, it brings two new interfaces. So Blink Web Media Source. And here again, so they are used in the render process, and our implementation here just forward all the function by APC to the media process. So the difference with progressive streaming is that we don't, in that case, we don't get data through the browser process, but through the render page, through the render process. For the source, we just almost copy-paste the one from WebKit because there is nothing almost of Chromium inside. It's a bin of app source, but there is ongoing work to have a GST multiple app source, so not a built-in element inside Chromium, but something as a GStreamer plugin in upstream. So encrypted media extension. So this is another extension, another JavaScript API. The intention is to support the DRM, so the digital rights management, in order to not use Flash plugins. So here it's a line. So you can manage a session request key and add a key to your video tag. There is no specific Blink interface. Choose the main one, but it has some new function. And on the media process side, we use the really cutting-edge features that have been introduced in 1.6, so about to handle the protection. So the element on the bottom left has been provided by Philip, and it's exactly the same that they use in the downstream branch of WebKit. So the good thing here is that this is really generic. We can reuse the power of GStreamer. So about about zero copy decoding. So first, what it is. So it's really simplified diagram. It's not the same use case every time. But if you imagine on desktop, you have your CPU and your memory, and you have the GPU and its own memory. If you decode with GPU, you want to stay all the time in the GPU memory. You don't want to download the decoded data to do some conversion or some copy around, because it's difficult in your application to manage the lifetime of this buffer. So sometimes you just copy because you are lazy, or you need to convert to another format, and then you upload again to the graphic card. So zero copy means basically you want to stay in GPU, then you have zero copy and real zero copy, where you don't do any additional conversion. But the problem with this, so first you have a bunch of hardware decoding API, like VA API, VGPO, V4L, and OpenMax. Problem with this is that we need to interoperate with GL. And if you take V4L, it doesn't know at all about GL. And GL doesn't know at all about V4L, but you still want them to work together. as we have a media process, so we want to do the hardware decoding in this process, and rendering in GPU process. So the final GL texture is in the GPU process. So you want you handle of the decoded frame to cross the process. We want this handle or the solution to be secure, because if you are in a protecting content case, if you have your encrypted stream, if you decode and then you just allow the user to grab the frame, you broke the whole chain of the encryption. You want that the input is the encrypted stream and the output is, for example, HDCP. So you still want to manage the rendering, but you want something secure under. So the solution, and we have experimented, is using DMA buffer. And we have also used VA API. So in libVA, you have a function on the left of VA acquire buffer handle. It allows you to export a VA surface to a DMA buffer. Then you get a file descriptor. You can cross this process, you can use the file descriptor in the GPU process. So it's a bit tricky. You cannot just send it, like make it with your own way visible to GPU process. You need to wrap it into a message for a Unix socket. So on media process, you will have, for example, one number, one integer, and on GPU process, when you receive this special message, you will have another number. Okay, and once we are in GPU process, we use an extension of the EGL image, so EGL image DMA buffer. This is in the Chronos specification. So here, in the diagram, we see that this solution it's only thing specified. It's not custom things. And this extension, EGL image DMA buffer, allow you to import it to EGL image in order to convert to GL texture. We have used a whole open source stack, so including the open source driver. So this diagram is to speak about, it's out of Chromium, but it's to mention that in Mesa Gallium, there are features that you may not know. But let's start with the left block. So you have libdrm, so it's not for the protected content, it's for the direct rendering manager. So this is an API that allows you to instantiate, create GPU buffers. So then you have libdrm for Nouveau for the NVIDIA graphic card, and you have libdrm Intel Radeon. And this is the low-level library that talks to the kernel driver. Then in Mesa, so you have, I call it pipe video. I'm not sure if there is an official name for it, but everything is prefixed with pipe. So you have pipe surface, pipe resource. It's an internal API to Mesa Gallium, and when you have a new driver, so you have a new libdrm, and the goal is to implement this interface by video with this libdrm. And then in Gallium, they use this API to implement all this backend, like vAPI, vDepot, OpenMac, OpenCL, and GL. So if you arrive with your own driver, you just need the libgrm and implement the pipe video surface, and you will have all of this backend. And then we use GStreamer, GL image sync for GL. And in our case, we to prove that zero copy is working, we use gstreamer-vaapi. So now in Chromium. So on the left, you have a media process. So we use GstPlayer. You imagine at some point you get a stream with, example, H.264. It will use GstVAPI decode. It will call the function to export to a DMA buffer. So we will go all the way down until to make the IOCTL call to talk to the kernel and to export your DMA buffer. And then, at the end of the pipeline, GL image sync will see this DMA, this surface which is exported to DMA buffer, and will import it into an EGL image. So we will call EGL create image. But here, the difference that we use the client-side API, so it's actually forwarded through IPC to the GPU process. So the real EGL create image in GPU process. This IPC was missing. All the GL call are serialized, forwarded like this, but not all for EGL. Because in Chromium, for the hardware decoder, they actually do the hardware decoding in the GPU process because it's easier to handle, especially the zero copy with different platforms. So there is already an object that wraps an EGL image, so GFX, GL image, EGL. This is a Chromium object. We just have implemented the IPC. And then, when it imports, it makes this IOCTL call to import the DMA buffer. And hopefully it's a success. So, the sequence demonstration. So far, we have now MSE, media source extension for YouTube, EME for encryption, and zero copy. So this is, I don't have YouTube here, I mean, I have not the network, so YouTube has its own set of conformance tests and performance tests. So and it's on the GitHub, so you can just grab it and put it in your own server. So for example, we just take one of the MSE performance tests. Okay. So this is using this client-side JavaScript API. I would have been happy to show you through YouTube, but I have not the connection. There is also a conformance test for the EME. So this is using ClearKey. So with ClearKey, it just helps you to make all your plumbing, but then your decoded frame, it's not supposed to be protected. So it's ClearKey. Okay, so I can do. I can also apply my hack to prove this is really media process. So yeah, the effect. So now I'm going to enable gstreamer-vaapi. I disable it just to make it easier, but now I'm going to show you 0 copy, so I need it. So now it's there. I don't know if I have the sound. Okay. So we had just pause, and to prove you that it's really doing 0 copy, there is a way to see the exported DMA buffer. You just need to. So I'm just looking for the PID of the two processes. So if you take first the media process, you just go to proc your PID number and FG, and it prints all the file descriptor actually available for this process, and you can see that there is the one for DMA buffer. And now for the importation for the GPU process. So I just grab the PID. But here you will say, okay, there are a lot of DMA buffers, probably a leak. But actually it's on purpose. I actually disable the, because when you import, you're then supposed to close your handle. But if I close, it's too fast, so it receives through IPC, through the Unix socket, and then directly import it. So if I really uncomment the close call, we won't see any DMA buffer. It's too fast.
Do you have fences over the IPC?
Fences.
Do you have fences over the IPC for GL to be able to fix that?
To fix what?
So basically, you send your DMA buff, but you need to track its lifetime. So in
Yeah.
your pipeline, you do your stuff.
Yeah, you have
with
yeah,
a fence,
you have fence.
and then you have some process that waits before giving it back to the buffer.
You have fence. I haven't pushed it to really see,
It's like a lot of work.
but the code seems to be there.
Okay.
And then, because after this last demo, there is still two last slides. Doesn't exist. This other tabulation. So what is interesting to see, it is there. So, okay, there is still an ongoing discussion about the caps feature about DMA buffer. I should rename it and make it the first part in capital. Even though the name is, yeah, it's under discussion. And you see here that it's imported to and then uploaded to a GL texture. Okay, so what are, in summary, for all, what are all the supported features? So far we have progressive streaming, adaptive streaming, and second part I showed you MSE for YouTube and to handle protected content. And also we have just seen the 0 copy working. So we need your contribution. There are some topics. First one is in the media process. We want to have some more abstraction layer in order to even support other backend, other API. So not only GStreamer, make it really without the GStreamer name. Really have a part only about media process. So I told about this already, this multi-app source element that for now it's built in Chromium, but we want it to be outside. About when you are using progressive streaming, we would like to factorize with a sub HTTP source or the one in WebKit in order not to implement a built-in element, but just a small interface. Then we want to, that would be great to try gst-omx on desktop. So in theory it's possible because Mesa Gallium provide you this backend. I never tried, but I heard it's in good shape. I never heard about someone trying it with gst-omx, maybe. But for sure it doesn't implement the OMX use EGL image. So actually it would be a good contribution to Mesa. It would be great to support WebRTC through the Open WebRTC, the framework to support it. We would like, in order to have our secure DMA buffer, experiment this open source trusted execution environment, so BTT. We don't know a lot about it, but we keep an eye on it. Would be great to fix this Pulse Audio crash with the sandbox. We only have tried on one platform. There is more things we can do to debug, but we didn't have time so far. If at least someone could try on his own platform with different versions of all the kernel and Pulse Audio, just tell us if it's crash also. And in the YouTube conformance test, the one I used to demonstrate MSE, it would be great to pass all the tests. It's a good way to find bugs. We need to fix them. Okay, so we have all of this is on our GitHub. And thank you for your attention. Do you have any questions?
Yes. I am working implementing MSC in WebKit, which is the other browser. And I would like to know one thing. How do you implement ffmpeg? If you just use the data provided by ffmpeg and pass it directly to your pipeline, or if you use the chunk demuxer provided by Chromium, which is what they use, and just buffer the data on your way, and then pass just the demuxer data to the pipeline.
Great question. So question is, do we use for MSE, media source extension, the chunk demuxer in Chromium, or do we pass the data directly to GStreamer? The answer is that we don't use chunk demuxer. Our point of view is that our idea is to reuse Gstreamer as much as possible. So when I described the existing backend, I didn't mention this chunk demuxer, but yeah, it's yet another custom implementation. Yeah, so we don't use it.
And do you use a single pipeline to do the pre-processing and then the playback, or you have a split pipeline?
It's only one. Yeah, good point. Yeah, it's important to understand that there is only one pipeline which lives in media process. I mean, for each Vido tag, it's not split across a process.
Because we tried with a single pipeline, but had so well, and we got basic playback working and so on. But then when we reached the seed feature in the UC tests, it was so complicated that we had to split the design in append backends.
Right. Good point about MSC seeking. For now, we don't support it.
The idea is that if you chunk your data in smaller pieces, it's easier to do seeking because it's some sort of
Right.
editing list.
Okay.
The smaller or you chunk, the easier. I think you'll have to do that eventually.
Okay. Yeah. That
It's the only way forward.
we are not close to any idea. We can even have support both and try and compare. Yeah.
Other thing we found is that with 6, QDMux behaves properly if you just append data in line, I mean, in a continuous way. But when you seek and when you jump to a different time, then QDMux sometimes doesn't behave properly because it stores the previous time and generates the next time stamps based on what was played last time.
So but do you think we can improve gst-omx or it's not possible?
Maybe, but I don't know if the required changes would be accepted upstream because this MSC use case is very specific.
That case, I suggest to yes. I suggest you contact upstream and discuss about it. Yeah. Is there any? Okay.
In my case, in my company, we are working, we are developing IP for hardware decoders, and we have always been using importing buffers from decoder instead of exporting. I think that you were suggesting to use importing from GPU instead of from decoder. In case of Android, you have Gralo, you let the GPU allocate the buffers and then you import the buffers for the decoder, for the output. Is it a better approach to do it the other way around for Gstreamer? We are trying to find the best possible solution. Some customers are using both ways.
So,
okay.
Okay. Is it necessary that I repeat the question or? Yeah. Okay. Yeah. Okay. So the question is: so far in the solution I presented, we export the surface from media process and we import in GPU process. Can we support the other way around, which means exporting from GPU process? So good question. So
because we are also using gst-omx.
Yeah, exactly.
To reduce the amount of work that we need to do
yeah, exactly.
use the same solution than Android.
Yeah. So with this solution, so you have the API decode.
I cannot
So you have the API decode. Okay, so that would be the last answer, I guess. So I demonstrate the API decoder, but with without any more change in Chromium. If we have the v4l decoder, it will work the same way. But for for OpenMax, yeah, indeed it will be different. You need to, as you said, export from GPU process and improve a bit the IPC we made, but we can use it to cross the process, but in the inverse way. And that's why I mentioned that it would be great to try gst-omx on desktop with Mesa Gallium and implement this OMX use EGL image to experiment this. But there is no blocking design. It's perfectly possible. We just need to try and prove that it works.
Okay. Out of time.
Mm-hmm.
We're out of time.
Yeah. Okay. Thank you.